In my previous lecture, I have already talked about the different methods of charging a body, the properties of charge, and comparison between charge and mass. Now, let's go ahead with the force experienced between the two charges, known as electrostatic force. When two charges are brought close to each other, they start experiencing force. As per the previous knowledge, like charges repel and unlike charges attract each other. And the expression for force is given by Coulomb's law, which says that the force is directly proportional to the product of two charges and inversely proportional to the distance square of the distance between the two. This proportionality sign can be removed by introducing a constant of proportionality, K. When constant of proportionality is introduced, force becomes K Q1 Q2 upon R square. This K is not a universal constant. It depends upon the medium, and it is given by the expression K is equal to 1 by 4 pi epsilon naught, whereas this epsilon naught is the absolute permittivity of free space. So, in place of the free space, if a medium is introduced, then this epsilon naught is denoted by simply epsilon, and it is the absolute permittivity of the medium, which is given by epsilon is equal to epsilon naught epsilon r, whereas this epsilon r is the relative permittivity, which is also known as dielectric constant, given by K. Dielectric constant is denoted by the symbol K. Epsilon r, or dielectric constant K, is the ratio of absolute permittivity of the medium to the free space. It is a dimensionless quantity. Force is 1 by 4 pi epsilon naught Q1 Q2 upon R square. It is the force when the two charges are placed in free space. This 1 by 4 pi epsilon naught is denoted by K, small k. The unit for force is Newton. Dimensional formula is mLT minus 2. Charge, its unit is Coulomb, and its dimensional formula is given as AT. This dimension formula comes from the concept current is rate of flow of charge. It is Q is equal to IT. Dimensional formula for current is A, time is capital T, so Q becomes AT. Dimensional formula for distance is meter. The unit for distance is meter, and its dimensional formula is L. Now let's find out the dimensional formula for K. From the formula, K is F R square upon Q1 Q2. The unit of K becomes Newton meter square per Coulomb square, and its dimensional formula becomes mL3 T minus 4 A minus 2. For the free space, epsilon naught has the value 8.85 10 to the power minus 12 Coulomb square Newton per Newton meter square. So, if I put it in this formula, K is equal to 1 by 4 pi epsilon naught, its value comes out to be 9 into 10 to the power 9. So, very popularly we use F is equal to K Q1 Q2 upon R square, and K is taken directly as 9 into 10 to the power 9 Newton meter square per Coulomb square. Now, let's try to imagine how big 1 Coulomb is. When two charges of 1 Coulomb each are placed 1 meter apart, they start experiencing force K, which is given by 9 into 10 to the power 9 Newton. If I compare it with mass or weight of an object, which we can easily see in day-to-day life, then it is the weight of a truck. It can be considered as the 10 to the power 9 times g. So mass can be compared as 10 to the power 9, which is 1000 times 1000 times 1000, and 1000 kg is known as ton. So it is the weight of 10 to the power 6 ton. If 1 ton is considered to be the mass of a truck, then it is 10 to the power 6 trucks weight. So when 1 coulomb charge each is placed 1 meter apart, it experiences such huge force. That means coulomb is actually a very, very big charge. As per the definition of SI unit, the size of the quantity should be practically used or can be practical in nature. So coulomb is taken as derived unit and ampere is taken as the fundamental unit. So as far as quantity is concerned, current is considered to be a fundamental quantity. So the charge coulomb has the dimensional formula AT. Force is a vector quantity. Charge is a scalar quantity. R is the position vector, but soon I say R square, it is R dot R, because R cross R is always 0. So R dot R becomes a scalar quantity. In this expression, right hand side is totally a scalar quantity. That means it indicates that this force is actually the magnitude of the force. K is also a scalar quantity. Now, how to express force in the vector form? For that, let's take the coordinate system. Consider charge Q1 is placed with the position vector R1, Q2 is placed with the position vector R2. What is the force experienced by charge 1 due to 2? We denote it by F12. This charge will get repelled from charge Q2. That means it is getting a force in this direction. If I show this direction of force with this distance or this vector R, then I can relate this R, call it as R12. With the help of triangle law of vector addition, it will come out to be R1 minus R2. R2 plus R is equal to R1. R1 minus R2 becomes R, and if I denote R1 minus R2 by as R12, if I call this R12 simply as R. Then force experienced by 1 due to 2 is K Q1 Q2 upon R square, and position it's a unit vector as R cap. It will be complete, showing as the force with a particular direction R. Whereas what is this R unit vector is the direction like this. Now if I consider force experienced by 2 due to 1, call it as F21, it will get repelled in this direction. And if this force is shown by the vector R21 direction like this, then this magnitude of R is exactly same as this magnitude of R, but here this R has direction like this, calling it as R12. Here the direction is this one. We have to call it as R21, which is opposite to R12. R21 is equal to minus R12. So if R12 was called as R, then R21 becomes minus R, and accordingly we can say F21 as KQ1 Q2 upon R square minus of R cap. And hence if I compare these two now, F12, all these terms are same except this negative sign, and hence F12 is equal to minus F21. Forces are equal and opposite in direction. Further elaborating it, F12 is equal to KQ1 Q2 upon R12 square with R12 cap. If I expand this unit vector in terms of vector, it is R12 vector upon R12 magnitude, and hence F12 becomes KQ1 Q2 R12 cube and R12 vector. Similarly, F21 can be written as KQ1 Q2 upon R21 cube R21 vector. Now writing this expression in terms of x, y, z coordinates. Let's consider this Q1 has the coordinates x1, y1, z1, and Q2 is placed on the coordinates x2, y2 and z2. Then R1 is x1 I cap, y1 j cap, z1 k cap, R2 is x2 I cap, y2 j cap, z2 k cap. R12 becomes R1 minus R2 given by this expression. What is the magnitude of this R12? It is x1 minus x2 square root of this quantity square plus this quantity square plus this quantity square, and hence R12 cube becomes expression like this. So if we write the expression for force in terms of its components, then KQ1 Q2 x1 minus x2 I cap, y1 minus y2 j cap, z1 minus z2 k cap, these two things remain common together. So the x component of the force is KQ1 Q2 x1 minus x2, and the expression is given by this. Similarly, we can write y and z components. What is absolute permittivity? Absolute permittivity is a measure of how electric field gets affected by the dielectric medium. Magnitude of the force in free space is given by 1 by 4 pi epsilon naught Q1 Q2 upon R square, but soon the medium is introduced between. Depending upon what is the medium, this epsilon naught is replaced by epsilon, which is given as epsilon naught epsilon R. Now we can see it is Q1 Q2 and this is 1 by 4 pi epsilon naught R square. So Q1 Q2 upon R square. In the denominator, this epsilon R remains like this, and this epsilon R is also known as dielectric constant, as we have previously discussed. That means I can write force experienced by two charges in the medium is force experienced in free space upon the dielectric constant of the medium. That means the force between charges will get affected due to the dielectric medium introduced between them. Now, one of the application is of a solution or electrolyte where the chemical is dissolved in water and it becomes easy to dissociate it. Pure water has dielectric constant K almost same as 80. So when a salt is dissolved in water, it gets dissociated easily. That is why electrolyte is a solution form. It is a salt dissolved in water, because the two ions will experience force given by this expression when there is no water between the two charges. But soon water is introduced. This K Q1 Q2 upon R square in the denominator dielectric constant gets introduced, and hence Fw becomes F naught by At. This force between the two charges has drastically decreased by this particular term, and hence in such situation the dissociation of the ions becomes easy, and hence often the electrolyte is in the form of a solution. Thank you for this particular lecture.